Hi, my name is Nick Jackson. I'm a professor in chemistry at UIUC, and I'm going to tell you a little bit about how once you have a machine learning model that you're going to use in a chemical context, how you actually assess how good it is at its job. So when you have a machine learning model, you usually have some set of data points. So here we have, say, n data points, n experimental data points, and you have some kind of measured experimental property value, which is y sub I. And then you have your machine learning model, which predicts some predicted value that is supposed to be as close to the experimental ground truth as you can. And so an extremely common error metric, an extremely common metric for evaluating your ML model is to take the difference between your predicted and your actual value and then square it and then average this difference over all of your data points. So this is called a mean squared error. It's pretty much the most common one in machine learning. There's another analogous or another related quantity that's called the coefficient of determination. And this is basically comparing how inaccurate your model is compared to the ground truth relative to the mean value of all of your data. So this is very common when someone says r squared. If it's r squared is 1, it means that you've perfectly fit your data. And if r squared is 0, it means your model is basically as good as predicting the mean. And if it's minus infinity, minus a very large number, it's very, very bad. So the question arises that if you have these metrics for evaluating how good your ML model is, if you have infinite data, should a perfect machine learning model make predictions with 0 error and an r squared of 1? And kind of ponder this for a second. If you think about it, the answer should be no, but it might not be obvious. So an example I like to use is in the context of predicting the melting temperatures of molecules. So you take a given small molecule and you then try to predict exactly at what temperature the crystal structure of that molecule will melt. This is a very common task in drug design. And so what you immediately realize, if you think about this as an example machine learning task, is that many molecules have many different crystal polymorphs, right? So cocoa butter is the classic example where cocoa butter can melt over about a 60 Kelvin range of temperatures. So if I just have one molecular structure and I'm trying to predict the melting point of a molecule, it can range by as much as 60 Kelvin depending on what crystal structure it's in. So the reason I bring this up is that if you were to look at the range of melting temperatures that are observable across crystal structures, you will get this nice graph on the left, which says that there is an intrinsic noise on your prediction task that you could never do better than if you're trying to predict the melting temperature of a specific molecular structure. So this is the idea that if you have infinite data, the quality of your prediction will still be limited by how much noise is actually in your experimental data. So this immediately raises the question of, well, how do you make sure your machine learning model isn't fitting the noise and is in fact fitting the signal that you're hoping for? This leads to the ideas of over or underfitting. Overfitting is the idea that you have a really complicated model that is fitting all of the fluctuating noise that's not the signal. So that's indicated by this dashed green curve on the left here. Your function is incredibly complicated. It's fitting and hitting every single point it can. And underfitting is the opposite, where you have an extremely simple function that doesn't fit the data very well, but it does not, err towards fitting all of the noise of the data points. So what one usually does to test how good an ML model is you fit your model on one set of data and then you test it on a set of data it has never seen before. So if I were to take this green curve on the left that fits pretty well and apply it to this new data on the right, you'll see that it actually is a terrible model because all these oscillations are completely missing the data points. They're all totally tailored to the training data on the left. Whereas this underfit model that was overall kind of bad actually is still pretty equally bad at its job for the new data, but it's not biased to, it's not, overfitting the noise in your data set. So the common strategy for avoiding this problem is to use what is called a training test split of your data. So imagine you have 1,000 data points in your data set. What you do is you split your data into two sets, and you train on one part of it, and you test your model on the other. So a very common splitting is 80-20. So I would take this data, I would just randomly split it down a particular part of it so that I have 200 testing data points. I would then get my model to learn on the 800, and then I'd evaluate how good it is on the test data. It's hard to overstate just how important this is for machine learning in chemistry. If you do not evaluate the performance of your model on data it has not seen before, it is effectively a useless model, right? This is the purpose of why you want a machine learning model in the first place, is to guide design and make predictions on data it's never seen. So intrinsic to having a good model is evaluating its ability to perform on data it hasn't seen. So as in the context of the previous model, or the previous examples I gave, you can split up your data. So here on the left is, say, all 1,000 data points. And I have 80% that's training, and I have 20% that's testing. And I fit on the left, and I evaluate the error, mean squared error, or coefficient of determination on the right. And that is an explicit measure of how good my data is, or how good my machine learning model is on my data, I should say. So this is a very standard approach. The last thing I'm going to wrap up with is what a slightly better version of this is. So what you could imagine is that if you randomly split your data, how good your model is on the data it hasn't seen is going to depend on what the random split you picked was. So to try to remove this random splitting effect on your model performance, there's an algorithm called cross-validation, which is basically training test splits but taken up a level. So k-fold cross-validation is you take your data set, you shuffle the data randomly, you then split it into a certain number of groups called k-groups. So let's say I have split it into 5 groups, so 5 folds. So here's one chunk of my data, here's another, here's another, here's another, and here's another. What I do is I train on, say, 4 of the folds, and then I test on this remaining fold, and that's one manifestation of my model's performance. Then what I do is I go and I train on these 4 folds, and I test on this one, and I record that performance. And then I iterate, and I just keep doing this. So now here I'm going to train on those 4 folds and test on this. And by iterating through this procedure, you remove the bias of this random selection of your data, and you get a model that is going to be robust against the random selection of your data in doing these training and test splits. And so the big idea here is that your ML model is guaranteed to overfit in most contexts by trying to learn the noise instead of the signal. So by having these training and test splitting algorithms, you can really guard against a lot of the problems. So I would encourage you to always keep in mind that all of your data, regardless of what it is, has some amount of intrinsic noise, especially if it's experimental. And so you're guaranteed to have some level of fitting the noise when you go to train your model. But you can really help guard against this by using train test splits and cross-validation procedures.